I'd like to start with, before I will announce the next speaker, I'd like to start with a well-known quote by Werner Vogel, the CTO of Amazon AWS. And he said, there is no compression algorithm for experience. Of course, you can treat this quote by your own way, but for me, it sounds like there is no way to start from some level and avoid all the mistakes. Of course, in our journey making, and we're still there, we're still running, we met quite a lot of different hidden pitfalls and some number of mistakes we made and still making, to be honest, right? And that's why I'd like to invite Levon, our head of solution architects. He will share his story about the large-scale training game. Thank you.
Hey guys, you can hear me well, right? Yeah, that's okay. So Vasily always knows how to put it philosophically in a very good segue. Really enjoyed it. So my name is Levon. I lead the solutions architect efforts at Nebius. And solutions architects are basically the people with the elbow grease. We basically just jump in and we try to get our users to be successful in the technical part of the standpoint. We basically try to help them achieve their goals and crush all the technical blockers ahead. We're basically currently a combination of MLOps slash general cloud native experience, which, as we see, is very much in demand in generative AI and ML public space currently. So the name of my talk is what it takes to win the large-scale training game. And today I'm going to talk about more from the side of how do you prepare everything for for going on training at a scale and not make the mistakes that we made assuming what is a large scaling game. And a small disclaimer, I'm of course not going to talk about how to optimize your PyTorch code. So please, if you're here for that, yeah, maybe stay for more infra stuff. Before starting, I would maybe go into understanding the audience a little bit more. So I might adjust my speech a bit. Can you guys raise your hands if you are into either ML engineering or MLOps or something of that matter, and you're running? Oh, okay, a pretty substantial amount. Is there also somebody, maybe a cross-section of audience, but maybe you're into academia? You come from academia or, okay, yeah, there's some cross-section. And is there business audience here who is on the commercial side, on the business side? Yeah. Are you? Okay. A pretty substantial amount as well. So I'll try to, another disclaimer, my talk is a little bit more chit-chatty rather than straight-up diagrams, but maybe this is something you would need after the very, very context-heavy separator talk of my colleague. All right. So again, let's look at Nebius, but look at Nebius a little bit on the user side, because I, as a solutions architect myself, actually represent more of a customer experience than anything else. So what we tried to do, when we created this neo cloud that is called Nebius, as Gleb rightfully put it, there was a long journey. And during this long journey, we kind of created a chimera of this is how you can, for a reasonable price and very optimally run your large AI workloads. At the same time, we'll give you a good public cloud customer experience. What do we define a good public cloud customer experience? First of all, it's user-centric approach. So you can interact with the platform using all the contemporary methods like Web Console, a CLI, an API, and a Terraform provider. We have our own. So you don't have to basically, here's your bare metal cluster. At the same time, we have a pretty detailed documentation, a public one, so all the knowledge is not basically saturated into a single engineer in your Slack channel. We have a built-in monitoring and observability stack, both on the level of like the deployments in our public GitHub and of course the like basic monitoring embedded in the platform. We have 24/7 technical support with an actual with an actual console, and just recently we added a Slack agent that allows you to create support tickets right from your Slack channel and interact it in a single thread. We, of course, provide GPU clusters. So basically, we gear up for war here really seriously because like Hopper architecture, we're one of the first adapters. We're kind of a like small, compared to like large hyperscalers, we're small on the radar, but we're one of the pioneering partners of NVIDIA in terms of their very expensive generative AI toys. And we will be also one of the first adapters of the Blackwell architecture, just like we were one of the first with the Hopper architecture. And we co-develop a lot with NVIDIA as per their, of course, reference architecture. Also, we try to build the infrastructure in a resilient way. So we're like cloud, as Gleb mentioned in the first talk, we're serial cloud builders. So all the best cloud practices, we really follow them to make the platform a platform and not just a piece of very, very expensive hardware. One thing that is actually differentiating us and is not this like kind of chimera thing, but pretty unique for us, we are dog-fooded by our own in-house AI team. So we have like a very strong internal ML team, some of them Kaggle grandmasters and like people who built some serious AI stuff even before the generative AI boom. And basically every big feature and every big new service is first dog-fooded by them. They suffer on it for a couple of months. They say what's wrong, we fix it, and only then we ship to users. And we, of course, try to give a good customer experience by not only like trying real workloads on the platform, but also giving a dedicated MLOps engineer to every large customer. Or not even large, I would say. If you're building something substantial, you will probably get an engineer who will be helping you. And helping you with like a lot of hands-on stuff. All right, so let me jump into kind of like an advent calendar of like what actual mistakes we made when we start playing this game. So Gleb gave you a lot of details and technical details on how we built the cloud platform and the stack, and I'll go more from the customer experience and how this whole thing turned out on the user side. So when we just started deploying and pivoting into the project GPU Cloud, which was not Nebius at the time, as was rightfully mentioned, we were thinking, okay, so we want to build a cloud for ML people. ML people right now want GPUs. So I guess if we build a resilient cloud and we cram some GPUs into a managed Kubernetes and basically give them like all this like Terraform, API, CLI stuff, they can just deploy it, right? Because like here's your Kubernetes, here are your GPUs, you can run it. So it should work, right? No. Actually, like, it failed, and it failed terribly. Our first users, their user experience was very, very far from excellent. So basically what we learned that day is that even if you have a frontier AI lab with like a lot of really, really experienced, strong people, the moment they're trying to do something on Kubernetes, this is like the end of their expertise and sometimes of their patience. So we also learned that the things that we think are very self-explanatory, easy to use, easy to deploy, it's not. Kubernetes has so many stuff that you need to like tinker with to manage to optimize your, to even run your distributed training on, that it's crazy. And the first users that were like trying our platform, like the amount of questions were just crazy. So actually our expectations faced the harsh reality of model builders do not want to touch the layers below any training workload or job orchestration. Their cluster preparation for them is time consuming, and honestly this is not the experience they're coming for. But at the same time we're like hitting a stalemate here in a way that, okay, there is like AWS, GCP, and Azure, and these guys have SageMaker, Bedrock, all this like services that they can run. And they're not running them because A, this is limiting, and I'll talk about it a little bit later, and B, it's very expensive. Like GPUs are expensive, and GPUs on the big providers are crazy expensive. So what we had to do in the solution here, we decided that, okay, we're going to build a chimera once again, and we're going to combine these two things. So we will give you Kubernetes, but we will give you the building blocks embedded in the managed Kubernetes itself. So every time you run a managed Kubernetes on our platform, you will get everything out of the box. You will get all the operators for network running InfiniBand, for the GPU, for everything. We will have an option of driverful nodes that basically hard code the most optimal driver version that we think you should run. If you don't, you can just basically install our own fully managed and fully patchable on our side GPU operator that will basically just give you all the versions of the NVIDIA drivers that we support. And we also will optimize all the inter-GPU, inter-network communications to basically just define the amount of resources you want in the managed Kubernetes and just run a job. So you basically, it's like a Lego, but for like smaller children. They think they're building something, but like the blocks are very, very self-explanatory. And we thought, okay, and we actually managed to see that the user's experience really grew. So we got our first users. These first users actually managed to launch some of their jobs. And then another question arose. So another expectation after the first one was, OK, model builders want GPU clusters that do not need debugging from day one. Like a lot of AI labs come to us and say, hey guys, we want healthy clusters from the get-go. We want to like go and like launch our distributed PyTorch job and everything would work. It's like, yeah, of course. So our expectation here was, like, if every component that we deploy to the end users is rigorously tested, unit tests, manual tests, whatever. If every building block is well tested, if we assemble it in a single cluster, it will work all together, right? Again, no. So after running with our first customers, and when they actually managed to win Kubernetes, it turned out that, like, if you put absolutely healthy building blocks together, they still fail. And it was like everything from correctable, incorrectable ECZK error, XID errors, GPU remapping, kernel panics, whatever. It just turned out that, like, the conventional methods of testing infrastructure building blocks, testing for training, just wouldn't work. If you right now would go and prepare a large training cluster for your end user and just test every separate part of it rigorously, I give you 90% that he won't be able to even persist a single full cluster job for even like half a day. So again, the painful reality was synthetic tests, burns, benchmarks for specific components are not enough to catch all the problems those model builders encounter when executing real workloads. It's, again, a disaster. They just come and say, everything broke down, our jobs do not run, what do we do? So the solution here, we decided, would be a pretty self-explanatory one. So in order for us to be able to give successful training to our users, we have to fully emulate our users. And by fully emulating, I mean not only running some like run-of-the-mill benchmarks or well-known benchmarks or even MLPerf well-known benchmarks. We're going to run end-to-end tests on every step from assembly line, where we basically build up our physical infrastructure in Taiwan, up to like specific shipment to a specific user when we're like basically just handing over the cluster. We're going to run everything we can, which can be similar to what the user is doing. So we're running nickel tests, ML Pro GPT-3 distributed training. We do a lot of MPI plus IOR storage tests for distributed training, like simulating how you would read and write data sets massively parallel. Another big part of it is, like, if we have a big feature, if we have something that we just want to bring to the users, we're not going to test it on the users. We have an internal AI team that basically would take this feature, put it in their own real-life training, live with it for a month, more often suffer with it than live in it, was a better term. We would basically do all the changes after their feedback, and only then we ship it to the users. That approach actually really helped us to improve the user experience by a large margin at that point. And we were already like pretty close to success. We were close to tier 1 for large-scale distributed training. But then we face another expectation. So, okay, now we have a functional Kubernetes engine. Now we have a pretty good amount of like real life, real scenario testing for every large cluster we deliver to our AI labs that are building their models. But we also now have an expectations that model builders want to large distributed jobs that don't crash. They say, hey, okay, your tech is good, your infrastructure is good. Now what we need is the jobs to keep persisting. We want our, like, the success criteria for now for large scale jobs is, hey guys, I want my job like taking, I don't know, 6K GPUs or 5K GPUs or 3K GPUs running for a week nonstop. And we were like, okay, so we got all the best engineering practices right now imaginable. We run real life tests. We like basically sometimes even deploy for the end users ourselves with our like solution architect or MLOps engineers. Now it should be persistent if we do all this, right? No. We saw that like the fail rate is still very, very high. So still, when we go into a I don't know, I think you cannot say it production training, but basically if you go into pre-training or training, especially pre-training jobs, on a large-scale cluster, it just blows up in your face again and again, no matter how much you test. No matter how much you test the GPUs fall off the bus. No matter how much you debug the InfiniBand or like the infrastructure, some links flap. No matter how much epoch training test runs you do, it still will always fail. So the painful realization was this distributed job don't scale linearly with size of the cluster. So no matter how much you rigorously test, it will fail. The reality currently is this just like, this stack is built this way. Like, if somebody tells you they can run a, like out of the box, they can run a large distributed training jobs on even a 1K GPUs, that's not true. So like achieving a stable environment for large scale clusters with just conventional methods currently is impossible. GPU meeting high performance computing is a disaster of an industry right now. So what do? Giving up is obviously not an option, so we decided to look at it from like another angle. So first of all, we decided that aside from reliability and resilience, health checks, self-healing, and automation, node draining, swapping, and predictive maintenance is the answer. We're approaching it not in a way that, okay, we have to make sure none of the GPUs will fall off the bus, or we will never get kernel panics, or we'll never get like problems with the underlying GPU to GPU communication network or library, but we're going to make sure that every time it fails, it's going to just like automatically heal itself. And the first self-healing properties we actually introduced in our separator. So in like the first version, like the separator ran some specific health checks like NVIDIA SMI, like nickel tests, periodically as a scheduled jobs, and if there were problems, it would basically drain a node. It will just say, hey, this is a bad node, it's not available for training. When we implemented that, we saw like a very large drop in failed jobs. We didn't stop there, of course, because our separator, as Kirill rightfully mentioned, is running over Kubernetes, right? So Slurm is just it's a very robust, but still a scheduling tool with no self-healing or like real orchestration features. But we have Kubernetes underneath. So what we can do is to separator to send a signal to our Kubernetes and compute engine to basically just, if it saw a drained node, it will take it out and put in a healthy one. And this is a big pro of cloud. No matter how good and resilient your hardware or your bare metal cluster is, it will never be able to basically unstrap a unhealthy node and strap on a healthy one in a matter of minutes. We managed to do that, and when we managed to do that, our failure rates dropped, I think, 2 times or something like this. So the jobs, at least like the time to live for the jobs, increased at least 2 times, and it was a very, very good experience. So at that point, we thought, okay, looks like we're there. Compared to all our competitors, our jobs fail either less or we're on the tier 1, because again, we talk with a lot of frontier AI labs. They're not, of course, running only on us, but also on our competitors. They're very they see a really resilient infrastructure and a lot of automation over it, and it doesn't bother them. So what else can we expect from a large training? So we think that model builders, having this cluster, they want full ownership of the cluster and ability to utilize 100% of the resource allocated. So they not only want all these things. Why wouldn't they, coming back to the AWS question, why don't they want just because implementing this, we're coming to something like a serverless service or some kind of a managed service like SageMaker or Bedrock or the respectful sec that GCP or Azure have. Why not just build that? And why not model builders just go into this? It's because of the aforementioned limitations. Whenever you want to run something really, really large on this big managed services, you will 100% of the time run into, okay, this specific framework feature does not work with our service. Okay, you're hitting some kind of, I don't know, internal network communications or, I don't know, some kind of weird black box issue that is staggering your runs. Okay, you're running a deadlock on your Python code, again, because something underneath of this black box does not work. This is still something you can work with and something you can live with if you're, I don't know, doing fine-tuning, RAG, and not very large-scale stuff. But large AI labs, they don't want it. They want 100% ownership. They want to see every line of, I don't know, debugging that's going on the cluster. So we were okay, we're not building this specific services. We're just adjusting to what large AI labs want. And if we provide them Terraform recipes, if we provide them cookbooks of everything that I mentioned beforehand, with all the automation, all the checks, it should work, right? No, again, so we thought that this would basically give us a recipe to success, but it just turned into a chaos of deployment time. So the time to train, how we sometimes like to call it, for the large-scale AI labs with this approach was really low. I mean, when they deployed the cluster, everything went well. But while they're deploying, while they're trying to set stuff up fully, it just, again, 5 times out of 10 blows up in their face because of the lack of experience, lack of expertise, lack of automation on their side. So what do we do here? Like, where can we also improve out of all the obvious steps that we take before? So we, again, face a harsh reality that frontier labs want to focus on applying their research, and they don't want this ownership. Yes, they want to see everything that is going on the cluster. Yes, they don't want a black box that would limit their code, that would limit their implementation, whatever. But at the same time, they want that, and they don't want all the responsibility that comes with it. They don't want to clean their jobs after finishing. They don't want to write, read the NCCL debug info information, why actually the communication didn't work. They don't want to monitor. They don't want anything like that. And basically, they just want, they're researchers, they're scientists. They just want to jump from one experiment to another without thinking twice about it. So basically, what was our solution here is to everything that at big training, everything that is a manual step, everything that is something that a researcher should do on his part of the shared responsibility should be automated. So we basically automate all the top layer management, including all the prologue and epilogue jobs. So not only now we take full responsibility for the cluster, we take full responsibility for the job scheduled on that cluster, no matter the framework. So we will help running epilogue, prologue jobs, we'll help setting up alerts, not auto-healing, and everything. After that, if the user, we see that a lot of users still don't want all the heavy lifting of deploying. We just kind of give up at that point and say, okay, here you go. Here's the engineer who will deploy everything for you. And we provide a very, very robust infrastructure as code, Terraform mostly, templates, and we run these templates ourselves. We deploy the cluster, and we hand over the cluster to the end user itself. Our expectation that even like if every part of the block, if the whole cluster has like a lot of automations into it, the user would be able and would want to run it, were not real expectations. There is still a lot of manual effort on the ML engineer, a lot of expertise, a lot of hands-on that should be done, and we now do it for our users, and we do it basically for free, fully. And this is our response to that problem. So basically, coming from like the step 1 to step 0, we basically go through just regular infrastructure, an expectation that a managed Kubernetes should just run, to a situation where we automate across the stack, give a lot of manual expertise of our engineers. And only in that case, we can really win the large scale training game. Large scaling game is a very new field. And everyone who ever tried to do this on a scale, I think would like agree with most things I say. So another action item on myself, if you have a interesting project that you want to run, if you actually are struggling with some of the things that I mentioned today, very high level, first join our Discord chat. Maybe you'll find some answers there. But also you can approach me, and maybe we can go into more like technical details on every of these high-level problems. Thank you.
Yeah. Just stay on the stage. So it's time for Q&A. Yes, please. There is a microphone somewhere here. So while we are waiting for a microphone, I have a confession, actually. So I have so much problems with these guys. They are frontline with the customers, and the answers, I really afraid. How many hours you slept during last few days? Sometimes the answer is 0. So they are the real front line to make our customers happy preparing the clusters.
It is a fun job.
It is.
Do you find the users have trouble with learning how to do how to dance your dance? What's the training curve for the user, for these data researchers, scientists?
It's a good, yeah. Basically, it's either a non-existent training curve, or they just hire somebody. So again, Nebius's core audience right now is model builders and like large labs. These large labs usually say, okay, we have like a lot of funding for people and a lot of funding for infrastructure. On infrastructure, we're going to go and rent out some GPUs in a form of a dedicated hosts or a cloud service, whatever. And we're going to dump all of our money for top-tier researchers. And when they come to like doing their stuff, they understand they don't have like any engineering, like infrastructure engineering capabilities. So, and they don't want it. The researchers are like, I haven't spent my, like, I don't know, 10 years on PhD just to, like, I don't know, read debugging reports from Kubernetes. So they either, like, aggressively push back, or they hire a MLOps engineer, and this is basically like a flavor of a person who, like, understands the domain expertise, but also for some reason has passion for infrastructure. This is, I would say from our experience, we lean more into people who just aggressively push back, and that's why Nebius has this unique approach of, if you're training something really substantial, if you explain it to us, and even if like it's not a very large scale stuff, we will provide you a fully free environment for you to like demonstrate us in terms of like your workloads, what are you doing, and we'll provide you again fully for free until you reach production a dedicated engineer who would like cover this. And in the future, who knows? Maybe he stays with you, maybe you hire somebody else.
Yeah, another question, please. And please shake your hand if you have any other questions. Yeah, please. Microphone there. Yes, please.
The question I had was about cross-cloud talk. Let's say I have a use case where I have a huge model that is very extensively data-driven and very huge that needs to be trained on Nebius, where Nebius could be leveraged fully, but maybe for cost reasons or whatever, I want to deploy somewhere else. Does that crosstalk, does that cross-integration work fine? What is that you provide with it? And also another question, maybe attached to that would be, what is the CI/CD approaches or methodologies that you would be providing? And also, at the same time, artifactories, essentially for version control or whatever.
Okay, yeah. So answering your first question. So one thing about this large-scale training jobs and like this generative AI workloads is they're completely stateless. And when I say stateless, when you're doing training, you basically don't have anything that is staggering you on a single platform. It actually like the best strategy for this kind of workloads, even if you're doing both, like training and then serving a model in an inference scenario, is to be multi-cloud. And we're like, as you said, we have like quite unhealthy love to Kubernetes on in our company. Basically, our whole platform is a Kubernetes on Kubernetes on Kubernetes. So like we're like, we heard you like Kubernetes, so we build a Kubernetes into your Kubernetes. And the cool thing about Kubernetes, and I'm tired of saying this word, is that you basically can deploy on us, and then just take your containerized workloads and run on GCP, run on AWS, run on Lambda, run on CoreWeave, whatever. Because everywhere you will find the same Kubernetes, the same kubectl, the same like deployment methods. Yeah, absolutely. But I would say you will hardly find somebody, like usually it's the other way around, because we operate on very, we own the full stack, and we have the ability, and we're not greedy too much, so we can provide you probably the best prices on the market. You can like check it out. And usually it's the other way around. Usually people come to train with us, and they either stay for other services, or they say, yeah, I have my architecture built out in AWS, but the compute there costs like a plane, so I'm going to do the compute on your side, which is also fair. In terms of CI/CD, so I wouldn't say we have like a lot of tooling around that. As you probably noticed, after the first talk, we had only 1 year to build our cloud, so you won't find too much. But like if you we have a container registry, and if you want to push your containers on our platform, run training, pre-training or training jobs there, and then run another cluster for like inference, or you would want, I don't know, do some data preparations on our platform, we have like tooling for that. We also have an amazing tool that we will be talking in further. It's called Tracto AI. It's basically like our own approach to like a fully managed end-to-end data preparation to model inference platform. And yeah, it's for the big boys, but if you want like a fully managed experience with like top-class engineers, you can actually just build a whole CI/CD pipeline using Tracto AI and never touching all the stuff I talked about. Yeah, it is basically a ready-to-go full service. You can wait till the Tracto AI talk, and you'll see. How smoothly does the whole thing around? Yeah, in a way, okay. Yeah.
Next question, gentleman here.
Hey, first of all, it was an excellent talk. Thank you so much.
Thank you.
My question is around, did you have any customers when it comes to large-scale model training prefer RDMA over Converged Ethernet versus InfiniBand? Could you talk a little bit more about the insights on why you chose to build the Nebius cloud on InfiniBand?
Mm-hmm. So, like, there are two reasons for it. Like, first of all, like InfiniBand is currently the creme de la creme of running GPU to GPU communications. And if we're talking about like large-scale training and large-scale distributed inference, for example, which is even more important after like the DeepSeek era came, the reasoning models that have like spew out a gigantic amount of tokens, etc. It's not even like it's shifting into like it used to be like everyone were after teraflops, but now it's not only teraflops, it's bandwidth. And the company that gives you the best GPU to GPU bandwidth wins. And currently, wherever you look at, InfiniBand is the fastest and the most reliable. Of course, you can give me the argument that, hey, AWS have their own stack. Google Cloud has their TPU stack that they're doing something else rather than InfiniBand. And that's also true. But from like, again, we're dealing with model builders. The reviews from the model builders or like the feedback from them comes in a way that, well, InfiniBand is either faster or we managed to make it work similarly in the AWS, but all the libraries above it, all the software stack and the debugging just really sucks. So like it's very, very hard to use something else rather than InfiniBand because it's not mature enough. Another problem is if you're prepared your distributed workloads for InfiniBand, like you basically built your containers using amazing NVIDIA software stack, and you can run it on every provider that runs InfiniBand, which are like basically the whole partner ecosystem of NVIDIA. If you basically did like, if you trained your model or you inferenced your model using TPUs, or you used AWS's stack, you're pretty hard stuck. Some people say InfiniBand is a vendor lock, and in a way it is because MLOps InfiniBand is NVIDIA's technology, but everything else is even more of a deadlock, except for is a vendor lock, except for maybe like DeepSeek guys who basically wrote their own collective communication library because they got GPUs that cannot run efficiently using InfiniBand. So yeah, the question, the short answer is it's just faster. The software stack is definitely not like ideal, but much better than anything else on the market, unless you're Chinese. Yeah, then you can do it.
Okay, the last question, gentleman.
Yeah, one quick question. So you talk a lot about the leading edge labs. What about for those of us who don't have infinite compute budget and everything that wants to do some sort of smaller scale pre-training or post-training or reasoning training?
Yeah, so that's quite fair. So basically, I would say Nebius right now really focuses on a large scale, but we definitely have a lot of what we call self-service clients, and that's why we basically built the platform to be able to authenticate via, like, I don't know, Google IDP or like GitHub, get access to the console, and just launch your workloads. It will be harder because in that case, we wouldn't be like jumping around you 24/7, but you have documentation, you have a Terraform provider, and you have a very explicit README on our public GitHub that actually is built by solution architects and developers. And we ourselves use it for the clients. We don't have a secret sauce. This is the same thing we have on our public GitHub. So if you are ready to invest a little more engineering-wise, you can cut on the budget.
Okay. Thank you. Actually, that's why I love Meetup format. So we are not on like a formal conference. That's why this Q&A part is, I believe, the most valuable thing. So big applause to my friend Levon. So.